Hello, class. I'm excited to start a new section with you. This is the section I like a lot. But this time I'm going to change it up a bit. And instead of giving a detailed derivation of diffusion from Gibbs free energy gradients, I'm going to just kind of skip ahead to kind of a different approach to deriving diffusion, and then just describe the Gibbs free energy equality as a driving force for it, and give you more of a pragmatic approach to just solving problems with it. I don't think in this case the theory is going to be incredibly useful at changing your perspective about how diffusion operates, but by analogy to vapor-liquid equilibrium, you can think about Gibbs free energy as a driving force for equality of material between phases. If you have a lot of different concentrations of a material, of a substance in a material, for instance, some sort of barrier, it's easy to use the same concepts from vapor-liquid equilibrium to ultimately think about how Gibbs free energy is a driving force that causes those particles to spread out. Instead, I'm going to go through a different type of derivation than is commonly done, but it's kind of nice. So consider particles that can move in either the left or right direction. So they can move left or right. Let's call this the minus direction and the plus direction. Okay, so then the particles moving in the minus direction would have the label P minus, whereas in the plus direction, they would have the label P positive. And the speed in the minus direction would be S minus. The speed in the positive direction would be S plus. And just consider that these are moving along a line. Normally, when class is in session, I simulate diffusion of the entire classroom, having everybody flip coins on a constant time interval and taking a step based on the direction of their coin flip. That is exactly the process right here that we are going to simulate with PDE equations. So moving along a line. So the PDE equation stands for partial differential equations. It doesn't stand for partially deranged engineers or fat dope engineers or anything like that. But you know, PDE is an acronym you can play with. So particle density moving in positive direction is P plus with speed S plus. And then particle density moving in the negative direction, moving in minus direction, is P minus with speed S minus. In general, P plus and P minus can have different quantities, and S plus and S minus could have different speeds. And we actually used this before in some research publications where we did have different speeds because of moving on dynein and kinesin motors in a developing embryo. So this is a very practical equation. One thing that's important for this process to understand it is that the particles that are moving around with these speeds can reverse direction with a certain rate. And this is according to a Poisson process. Okay, memoryless, lambda plus and lambda minus. Okay, so this lambda plus is the rate a particle moving in plus direction changes direction, changes to going in the opposite, changes to minus direction. And of course, lambda minus is the opposite. So if we take our standard accumulation equals in minus out plus gen minus consumption, balance to this, we get two equations for the movement of these particles. So these are, because things are moving in space and time, we have to account for that. So we have that partial of the particle is moving in the plus direction with respect to change in time. So what is this distribution doing? Recall P plus the density can depend on both the position and the time. Plus, we have to account for the fact that the particles are moving. And the way that we do this, that the particle density is moving to the right with speed s plus times p plus with any gradient in that velocity, partial x. So this term right here accounts for just the flow, the movement, as these particles are moving around and the particle density is moving around. And this is equal to minus lambda plus times p plus, because when you lose a particle traveling in the plus direction, you lose it with rate lambda plus, at which point it starts to move in the other direction. Okay, and then plus you gain some that are moving in the left direction and then change direction to become moving in the right direction. So we have equation 1, we have equation 2, which is the particle density in the minus direction. But here we have to account for the fact that the speed is pointing to the left, hence the minus sign for the speed moving to the left. Okay, now this, after a particle moving in the plus direction changes directions, it becomes a particle moving in the left direction. So every one you lose from the plus, you gain in the minus, and vice versa. Minus, lambda minus, p minus. These are the equations for particles jumping around that you can use to figure out something that looks like a diffusion coefficient. And we're going to have another way of deriving it, the more classical way of deriving it, in the subsequent video. But it's helpful here. We can make some definitions here and some assumptions to take some steps. Okay, so consider the total particle density. You know, if you're looking at a material, you don't necessarily know how many of them are moving to the left and to the right. You just see the total amount. So we can say particle density at x and t simply equal to p plus x and t plus p minus x and t. That's the total density of particles, incorporates all of them regardless of the direction that they are moving. But what about particle flux? The direction of the net movement of these particles. We can define the particle flux as the difference between the speed times particles moving in the positive direction minus those that are moving in the opposite direction. Okay, so now we have two new definitions. 3 and 4, we have the total particle density, we have particle flux. Now, let's go through a simplified system. Let's suppose this is where things change between this derivation and what I used in previous publications, but you can always go back to this. So suppose that the speed, the value of the speed is the same in both directions. So particles moving to the left and the right jump around and move in those directions at the same speed. And also, let's suppose that the frequency at which they change directions is also equal. And we just say that this is lambda plus is equal to lambda minus. So how can we use these equations to understand what's happening for getting a diffusion coefficient? So we starting from these two, we can think about what happens if you add equations 1 plus 2, what happens if you subtract equations 1 and 2. We get two different things. If we add them together, we add equations 1 and 2 together, we can then use our definitions to get a simplified equation. This becomes particle density over time plus partial j partial x is equal to 0. If you look at these equations, you can see that if you sum them together, these terms will all go away, and we'll introduce exactly the derivative of the flux. Okay, that's a very useful derivation. Now what about 1 minus 2? If we do 1 minus 2, we get a different equation. We get del J del T. So how this flux is changing in time, plus 2 times lambda J equals minus S squared del P del X. So if you take the addition of the equations and the subtraction of the equations, you end up with these two new equations that take advantage of the definitions we have. So this first one is saying particle density over time depends on the gradient of the flux. We're going to see this exact equation again from a completely different derivation. And then we have in this one right here, how the flux measurement, how the particle movement is changing in time. And we have this weird term over there with S squared and dp dx. So what do we do with this? Well, if you remember the property of commutative of derivatives, you can take this first equation and take the derivative with respect to t again. So we're going to do this. Take del by del t of this entire equation, because we're going to try to get it so we have terms where we can start to eliminate things based on the values of the derivatives. So we take del by del t of partial p partial t plus partial j partial x, okay, in this whole thing equals 0, because the derivative of 0 is 0, which gives you partial squared p over partial t, some sort of acceleration term, equals minus partial by partial t of del j del x. Now how does this help us? Now what happens if we were to do a similar operation to this equation right here? Okay, so what if we do partial, so this becomes a useful equation that we can use later for simplifying. Now what if we take partial by partial x of the other equation? So take partial by partial x of del j del t plus 2 lambda j equals minus s squared partial p partial x. Okay, we do this operation. We're going to end up with partial squared j. Well, I'll leave it in the same notation. We'll just do partial by partial x of partial j t. Okay. Okay, plus 2 lambda partial j partial x equals minus s squared, okay, del squared p over del x squared. Okay, so now we have something. We have a similarity in these two equations. Right here, this term right here and this term right here, we can eliminate using that just by substitution. And so we end up with a new equation for this system that is del squared p over del t squared plus 2 lambda times del p del t equals s squared del squared p over del x squared. So s, of course, is the speed. Okay, now what do? Multiply by 1 over 2 lambda. This is where things get really interesting. We have to have a condition on that, but we'll do this operation in steps. Okay, so we're going to have 1 over 2 lambda del squared p over del time squared, okay, plus del p del t, okay, equals s squared over 2 lambda del squared p over del x squared. Okay, so take limit that the frequency of the changing direction becomes very fast. And this is absolutely a function of temperature. Temperature increases, the molecules bounce around, they're going to change direction faster and faster and faster. And in fact, it is a very fast process. It's molecular motion. So as lambda tends to infinity, let me make a better infinity. That's a pathetic infinity. So lambda tends to infinity. You have to do it in such a way such that s squared over 2 lambda, so the speed of the particles is high as well, approaches some constant. Okay. In which case, this first term goes to 0 because 1 over 2 lambda, it becomes a very small number. So this leaves us to del p del t equals s squared over 2 lambda del squared p del x squared. This is pretty cool because we started with particles bouncing around, moving in different directions, and end up with an equation that looks like something we've seen before. So this right here is the equivalent of diffusion. So this del p del t equals d del squared p del x squared is with d defined as this ratio of s squared, the speed squared, divided by 2 lambda. So when you have a process where molecules flip directions and they all have the same speed, you can get an equation that looks like this, which is really similar to an equation we've seen before, which is alpha del squared temperature over del x squared. So d has units of length squared over time, as does thermal diffusivity as units of length squared over time. So the mathematics behind solving these is exactly the same. And the process that we looked at for how heat flows by conduction is completely analogous to the process for particle movement, and both of them are driven by differential Gibbs free energy.